which is on page 111. Ooh, lucky. It's approximately workbook problem 6.47 if you have an older version. Somewhere around page 110, 111, somewhere in there. On page 111. All right. Let's roll it. And I got this and this. All right. And so I think a ball on a string is a good place to start. Let me make sure the camera's working on both sides before I get too far ahead of myself. It's good. All right, so imagine you have this ball on a string. In this case, a lot of information can be learned about circular motion by thinking about this simple example. In particular, is the speed of this ball on a string constant?
No.
No. Where is it going fastest? At the top or the bottom?
Bottom.
Bottom, right? Roller coaster speed up as you go down. We'll talk more about this in chapter 8. But the idea here is, all right, that's cool. Now, notice this scenario. The ball is moving in a circle. Is this constant velocity?
No.
Is it constant speed? Yes. So here's a case where the ball is moving with approximately constant speed, but again, velocity is not constant.
Direction.
Direction is changing, right?
Yeah.
So one of the weirdest parts about circular motion is we have to constantly be thinking about what constant speed means. And even if you have constant speed, you may also have acceleration. In particular, let's actually do this first problem. Look at 6.47 before we do any other work. It's on page 112 for me. Okay, we're talking about circular motion. I'll do a bunch of definitions after we do this first problem to get some insight. Okay. We have a circle. It's like the ball on a string. And then in some scenario, let's say V initial and V final have the same magnitude, but these changing directions. All right. Now, from this problem, I know that acceleration is equal to, whoops, delta V vector over delta T. Well, in this case, that's going to be V final minus V initial over delta T, right? If there's some small amount of time it takes to go from this point to that point, that's delta T. Now, just to make this look a little bit more clear, I'm going to say that's V final plus negative V initial over delta T. Maybe that makes it worse for you, but the idea is this is V final. If I start right here, if I take V final and I add to it negative V initial, well, if this is V initial, the opposite of it is negative V initial. So that's adding to it this. So look carefully here. This is not V final plus V initial. This is V final plus negative V initial, right? Do you agree that this is delta V? Take a second. V final plus negative V initial should be delta V. What direction is the acceleration? Downwards. So in this case, when you have constant speed, the acceleration points, I'm going to say it another way, towards the center of the circle. Cool? And this goes to your point right there, right? You were saying, oh, the direction changes, right?
Yeah.
So here we see the acceleration is not changing the speed, but it is changing the direction a little bit. So we do get this. All right. There's a big if here. If constant speed. So if you have constant speed, acceleration points towards the center. So far, so good? Look at 6.48. In this case, we have some circular motion. We're again concerning 2 points near the top of the circular motion. V initial is small, V final is bigger. So V initial is right here. V final is a little bit bigger. I'm trying to draw that approximately to scale, but it doesn't matter too much. Basically, make sure V final is obviously bigger than V initial, or you've got your little handouts there. You could just use them. For this one, just draw right in the book. Well, we could do our same trick on this one. If this is V initial, this would be negative V initial. And notice, delta V points this way. And then I'm going to get in here so I can see better. There's the center of the circle. I want to point out there's some acceleration going this way and some acceleration going this way. Do you see that? If I draw these with dotted lines, maybe it makes it a little more clear. The idea is this is the acceleration vector. And what we typically do with circular motion is if you're not moving at constant speed, we split this acceleration into two unique parts. This is a portion that points towards the center. This is a portion that points tangent to the circle. So the acceleration vector is now some amount inwards plus some amount tangential. Okay? And here's where different textbooks are very finicky about what they use, all right? In particular, it would be cool if we could just use these words inwards and tangential all the time, but you know that's going to be a slow process to have to write that all the time. So now we're going to introduce new types of coordinates, all right? And I'm going to discuss this at length, but for right now, inwards is going to be minus r hat. That means radially inwards. Okay? And then in math class, maybe you know that theta is typically the angle, right? So this is going to be called theta hat. Theta hat. A few subtle points here. We are going to learn that the magnitude AC is v squared over r, where r is the radius of the circle. Now, I want to point this out. Is this number going to be positive or negative? Is v squared going to be positive or negative? Is a radius positive or negative? Positive. So AC is positive. In other textbooks, you might see a subscript r, which is equal to negative v squared over r equals negative AC. Some other textbooks, and I'm telling you, it's about 50-50 here, depending on which level of math you're at, etc. A lot of times they'll take this minus sign and group it up here. So another way of writing this would be A equals AR in the R hat without the minus sign, because the minus sign's right here, plus A tan theta hat. They are both good ways to do it. However, we're going to be doing some physics problems, right? And we like to do force problems, so we're going to do some free body diagrams. And one of the things that we have been doing in our free body diagrams is we'll show the direction of acceleration with an arrow and then write the magnitude of it. So we're going to tend to use AC. Does that make sense? In a dynamics class in engineering, you tend to switch to this mode. Good? All right. Now, you might not be familiar with these symbols, R hat and theta hat. So maybe I'll talk about those. And 6.49, you can look at that one later, but let's go back here. Let's go back to page 111 now and see if some of this notation makes sense. So it's just a ton of notation. Okay. And some of you have been like, I haven't had to practice too much. This is the chapter, this is the moment where it's like, okay, you really need to start practicing a lot. Okay. So to be clear, R hat equals radially outwards. Negative R hat equals radially inwards. That's just a convenient way of describing the direction radially outwards or inwards. So if you hear me say R hat or negative R hat, that's what that means. And if I could draw a random point in time in the first quadrant, sometimes that helps elucidate what these symbols mean. All right? If you picked a random spot out here, this would be the R vector. And you know that R vector is equal to X in the I hat plus Y in the J hat. We're going to just do 2D for right now. Right? If this point was at some point X, Y, V over X and Y. But now let's layer in this. This is going to be the angle theta. Typically in a math class, it's from the positive x-axis going, what is that, counterclockwise. Now notice this side is R cosine theta and this is R sine theta. Take a second to believe that. In particular, the notation. Notice I removed the arrow, so this is magnitude, right? Notice that R hat is equal to, get out of the way in a second. It's just the R vector, which is the X plus the Y, divided by the magnitude. What drops out? So notice R hat is equal to cosine theta in the I hat plus sine theta in the J hat. And this is one that I have memorized, and I use this periodically. Okay. And now to be clear, this would be R hat, right? A unit vector. It's not right. If you had a 25-meter radius, the R vector would be 25 meters long, but R hat is only 1 unit long. Think about it. Cosine squared plus sine squared equals 1. So this is a unit vector, 1 unit long. Everybody cool with that? Now, theta hat, do you agree if we were drawing this circle, theta hat would be this way? Right? It would be tangent to the circle. And now check this out. Notice theta hat is going to the left and up when we are in the first quadrant. Now we could spend some time doing geometry on this. If this is theta, this is 90 minus theta. Well, if this is 90 minus theta and this is 90, that makes this theta. If you didn't catch all that and that's too small to read, who cares? This is what matters. This is how I remember theta hat. The sines and cosines switch, and the I hat gets a negative. So it's negative there we go. So far, so good. Now, to be fair, we aren't going to use these a ton in this class, but as Jules knows, we used them a lot in 163. And if you're an engineer, oh my goodness, you're going to use these all the time. Okay, if you're in a Calc 183 or 184 class, you're probably going to use them as well. So it doesn't hurt to be aware of them. So far, so good. Again, we're not going to use these two equations too much, but we will in the future. That's why I'm showing them to you. All right, and I think those are all written right there. I hope that picture in the book makes sense of that. All right, so now some other terms. And again, I know they're all listed for you, so you could just add notes to there. So a lot of times we're going to call directions clockwise, so we don't have to use theta hats and stuff. We've got CCW for counterclockwise. So instead of having to use theta hat and R hat, I'm okay with using the symbol CW for clockwise and CCW for counterclockwise when we're doing circles. There's another symbol. Now I use what's called a double T. So we've got so many letter T's in physics. I try to make the one for period special. The period is the time for single orbit or single revolution. Hopefully that squeezes in there. Okay, thanks. So the period is the time to go around one time. Now we're going to see some other symbols. We already talked about tangential acceleration. We're going to talk about tangential speed. And for the most part, in this class, we're going to talk about circles with a fixed radius. But it turns out, if you're in a dynamics class, the radius of a circle could change, right? Think about this. If you're spinning this ball, and then I just start pulling the rope in, right? There's a speed towards the center as well as around. We are not going to do that. We're basically going to use standard radii. Or fixed radii, excuse me. So in our problems, we're not going to have to worry about the radius changing during the motion. In dynamics class, obviously you would, right? Think about how a cam works in an engine, right? The radius is constantly changing. So yeah, anyways, there's times where that's important. Fortunately, not us. All right. We've already talked about atan, a radial, AC, and I think we've got, oh, this is a subtle one. I'm not even going to say the vector. Notice, let's underline these words, speed, okay? And this is very subtle. Okay, if your speed is constant, there's no atangential. Remember those pictures we drew on the board a minute ago over there, right? If we have no change in speed, the acceleration was all towards the center. If the speed is changing, then you have to worry about this atan. Got it? So I want to be clear, and this is what I'm trying to emphasize, if this makes sense. Atan is not the derivative of the velocity vector. You see the difference? This is the deal, right? You have to take the derivative of the speed, which is not the same as taking the derivative of the velocity. Acceleration total is equal to ddt of the velocity vector. This includes both tangential and centripetal. Enough said on that? You bored yet? Yeah. All right. Just trying to, okay. So keep in mind where these terms are. If you get lost on a question when we're working, you can see we've got a lot of fun toys today. So let's get to it. Ooh, let's start with 6.51, everybody. I'm going to try and get a simulation going here. 6.51. Come on. Oh my gosh. So I'm trying to, if you're on Zoom, I'm just trying to get a simulation running. You guys take a look at it. Talk with your neighbor as much as you want. Okay? Talk out loud, run out of the room screaming, whatever. So again, 6.51, and I'm going to get the monitor turned on. I know you're kind of quiet right now. It's more fun if you talk and just say, this is what I think. What do you think? Just babble a little bit. I'm not going to make you. Probably don't need these today. I'll open up the laptops as well. At any point you want one, I'm not offended if you just get up and walk over in the middle of class and grab it. Okay. Hopefully I'm sharing screen. All right. So the idea is this. You could take a look up here at the main screen if you want, or on the screen if you're on Zoom. We're just going to let this pendulum swing back and forth. And I'm curious, what do you think is happening to the acceleration at these different points in the swing? And so to be clear, we're going to start over here at just some random angle, and then we're just going to swing it once, and let's do it in slow motion here. We're going to swing it in once. So for the first pass through this motion, right up to the other side, and then stop. Okay. All right. So in this case, let's say we're at this first point right here. What direction is A tan? And how big is it for point 1? So if we're sitting right here, what do you think? Anybody, take a guess. Is A tan 0 or is it not 0? Why do you say not 0? What does A tan mean physically? It's change in what? Change in speed. At this moment, do you think the speed is going to remain 0 or will it change? It's changing. So which way? This way, right? So there's A tan. All right, what about AC? What direction is AC? What does the subscript C mean again? Towards the center. Okay, how fast are you moving right there at that instant? How fast is this moving when you release it from rest? 0. What's the equation for AC? What was it? Do you remember? Yeah, if V is 0, what's AC? So there's AC is 0. Does that make sense? So that's what we're going to try and do for all of these points as it goes across. Did that make more sense of this question? Okay, take a second, take another 30 seconds to take your guess what it's going to be at the next point. Okay? And I'll run it to the next point. Right about there. So at this point, what do you think is going to happen to AC and A tan? Then at this point, I'll give you 30 seconds here. Just think it through. Alexis, is that showing up okay on the share screen? You can dump it in the chat if you want.
It is. Yeah, it is.
Okay, gotcha. Gotcha. Thanks. What do you think? Should we try the next point? Or did I give you enough time? I don't know. Or do you need another second? Oh, I see some people still writing. I'll give you 20 more seconds. Sorry, I have no idea what the time is. Ah, where's the clock? I'll just watch it there. All right, let's go for it. And I apologize if I'm cutting you off. At the next point, what should happen to AT?
Increase.
What is that? Say again.
Increase.
Why do you say it increases? What's the thought process?
Well, it's accelerating downwards due to.
So it's speeding up. Do you
Yes.
agree?
Yes.
Okay, so it's moving faster, but ATAN is not directly related to the speed. It's related to the rate of change in speed.
Okay.
So let's start with there. You said it's getting faster, right? So what happens to AC?
It gets bigger.
That's got to get bigger. Which way does AC point?
To the center.
Towards the center. So there's AC. Now let me ask you this. As you go towards the bottom of the swing, are you going to accelerate more or less?
More.
Why do you say more? How about at the very bottom? If you're at the very bottom of the string, you got a string straight up, you got tension up,
Okay.
MG down. How many forces are left, right at the very bottom? Let's go to the very bottom.
Just two.
Yes, at the very bottom, right, there's going to be tension up, MG down. How many forces left, right at the bottom? None. So how much acceleration left, right at the bottom?
None.
None. So that means down here, what's ATAN? What happens to the speed at the bottom? It's at its maximum, so AC gets even bigger. Now use that to fill in the gap. What do you think should happen to ATAN at this midway point right here?
Get smaller.
It's going to decrease, right? The thing is as you swing downwards, more of gravity is canceled by the string. So you're still getting faster and faster, but at a slower and slower rate.
Oh,
You see what I'm saying?
yeah.
You are still getting faster, AC is still getting bigger, but ATAN is actually shrinking. Ah, the joys of physics. You know what I'm saying? What's going to happen on the other side? How will the other side be different? ATAN points the other way, everything else is the same, right? So then here, ATAN would be biggest, and AC would equal 0. Sorry, it's so sloppy, but AT gets big. All right, so you ready to see this run and look at the vectors? Let's see if we could do this one now with the acceleration vectors. And so remember, when we do this one, at this point, right, there's some acceleration this way and some acceleration this way, and no one can see yellow on white. So let's try to make that a little bit more orangey or something. Right, there's a component like this and this. So go ahead and watch these as this runs. And I'm going to undo those last few just because they're messing this up. Let's just run this and watch it. So notice the acceleration is straight towards the center. It's all tangential. It's all centripetal. It's all tangential, going back and forth. And if we watch the velocity in addition, notice the velocity is always tangential. Do you see that? Because we don't have a component of velocity towards the center here. We don't have a radial velocity. We only have V10. Is that making some sense? All right. This gets tricky. Just a ball on a pendulum is somewhat complicated. Do you agree? All right. All right. Let's stop that. All right. So that was that question. If you want, you could go back and look more at that question, but I want to move on. And I want to start doing some math with numbers here, all right? So let me get rid of this. And then what do I need to do? I need to do this, sorry. Then we're going to look at 6.52, page 114, 6.52. Okay, we're going to try and analyze that ball on a string correctly. Am I going too slow or is this about right? Okay, about right. I'm going to erase the board on Zoom in case you're wondering why I'm not on screen. I'm going to erase the board real quick. And again, read what problem was that? 6.52, top of page 114 for me. Start drawing it on your paper if you want. Still erasing on Zoom. I was smart. I should have erased while you guys were working. My bad. So I'm probably going to gradually increase the speed, but I'm going to try and start kind of slow. 152. Okay, so this is kind of like our tennis ball. We got some object on a string. That's correct. We got a fixed length, so the mass 0.200 kilograms. I'm just getting all the important stuff on the paper. Do we know the length?
No.
That's L.
Oh, and it also says later it's 1 meter. Do you agree?
Oh, yeah.
Probably inefficiently written, but whatever. Sorry about that. And then it says theta is 30 and V is 5. Put a third sig fig on there. I'm assuming that's meters per second. Let me just check. All right, so that's the information that we have. All right. And again, don't overthink it. Imagine it's this ball, right? It's going like this. So I'm going to assume, did it say which way the ball is moving?
Yes, counterclockwise.
Counterclockwise? Okay. So that means the ball's moving this way. Thanks for that tip. And remember, do you agree that the velocity for our problems is going to be tangent to the circle? All right. And I think in the problem it also showed this angle is theta. Okay. What pushes the ball to the outside when I'm swinging it around? It's a trick question. What pushes it to the outside? How much can you push with a string? None. So there is no push to the outside. What is the string doing?
Pulling.
Pulling. What is the name of that force?
Tension.
Tension. So there's no push. Strings can't push. Well, you can try, but it's not going to be very effective. Unless you use like a whole bunch of starch or something. I don't know. Are there any other forces acting on the star? I'll wait for it. MG, excellent. And now, here's where all our work with these silly little inclined planes can finally pay off. The coordinate system that we're going to use should be aligned with the center, right? We want one of our coordinates aligned with the center. The other one's perpendicular to it. You see how this looks a lot like an inclined plane problem? That's not very good. I'm gonna show you a little bit. Just so I can see it better. Well, what's this angle right here that I'm pointing at?
30.
This is 30. This should be 90 minus 30. Do you see the triangle? So this part would be 30. So this would be 60. So what's this one? 30. And I'm just going to call it theta for right now to kind of get in that habit of doing it algebraically. Is everybody okay that if this is theta, this is 90 minus theta? Sorry about that. Okay. Watch this really carefully. Is this correct? Splitting it into components. Not parallel to the, okay, so that's wrong. We've got to make sure the hypotenuse should always be the longest part, right? The vector itself has to be the hypotenuse. So this is going to be an mg cos. This right here is going to be mg sine. And now I want to talk about these coordinate systems. What's a good name for that way? What's that way called? What was the unit vector we used to describe that way?
R hat.
R hat. Now, I am going to use this notation. I'm going to call this C hat for towards the center. This is not standard. I'm going to be clear. This is not something you're going to see in a lot of physics books. But for me, C hat is essentially the same thing as negative R hat. And I just like using this, so I apologize if you don't like that. The reason I do that is so that I don't get a bunch of negatives on my forces. That's all. Okay with that? If you want to know more about this in coordinate systems, the very last couple of pages of this book talk all about this. We can discuss it more next time. For now, let's do this. Which way is this thing accelerating? So we've got this and we've got this. I'm going to call this C hat. I'm going to call this tangent hat or theta hat, right? Do we know which way this thing is accelerating? What's that?
No.
Okay, you say there should be some component downwards. Do you agree that would be a tan? It's moving in a circle. Is there a component towards the center? Nod your head and say yes, because if it's moving in a circle, there's always AC. So the net effect is something like this. So this is a total. The total acceleration will have two components when we're in a vertical circle. So far, so good? All right. Well, in this case, and I should be clear, some people might draw a tan pointing the other way and we'll get a negative answer. Some people are going to draw this way and get a positive answer. You have some choices in which way you draw these arrows. So if you draw your coordinate systems and label stuff, I should be able to interpret your work. But it's crucial, now that we're moving in circles, people may actually make different choices on their coordinate system. Some people might call this way tangent, some people might call that way tangent. So it's important that you show your work so I can follow. Okay. All right, so in this case, give me the sum of forces in the centripetal direction. Somebody give me one force centripetal.
T.
T, I love it. Positive or negative?
Positive.
With positive centripetal, if we had done R hat, it would be negative. Okay, what else? Anything else or not? Mg sine theta, positive or negative? Use that arrowhead. Positive. That's it. So it's mass. Should I use positive AC or negative AC? Based off this coordinate system.
Positive.
Positive AC. To be clear, if you had used the radial direction, think about it. Do you agree we get negative T minus mg sine theta equals m times minus AC? If we had used the other direction, everything would get a minus sign. Do you agree? That's what I'm saying. Some people might do it this way, some people might do it that way, whatever. Same equation if you multiply by -1. How about the sum of forces in the tangential direction that I happen to choose? Somebody give me one force in the tangential direction. Mg cos, positive or negative here? According to this coordinate, it is negative. Negative. That's the only one. What about A tan? Should I use positive AT or negative AT? Negative AT, because it's pointing opposite. So this is actually a lot like this one here. We can see that if you screw up one minus sign, you could be in for a long day. Now in this one, check this out. We have already learned something cool. Look at this. What do we get canceling out in this equation? Mass, and we get A tan equals G cosine theta. You agree? And this probably makes sense to you if we put in some different angles. Can you see that if I write this low, or is it kind of bad? Tell you what, I'm going to do it up top. I'm going to erase this equation because we don't need it, okay? We've already got it. So let's look at this. If theta is equal to 0, 90 degrees, 180 degrees, or 270 degrees, just do me a favor, right? And let's plug in for A tan. Now don't worry about it. What's cosine of 0? Okay, so it's just G. You agree? What's A tan at 90 degrees then? 0. Which other one is 0? At the top and the bottom of the circle, we have 0 A tan, just like that little picture we drew a few minutes ago, right? What's it going to be here?
Negative G.
Negative G, right? Because you get a -1. Now think about this. What does that mean? Right? If we draw this picture, on this side, it's G downwards. Now follow this coordinate system around to the other side. Well, on the other side, based on our coordinate system, is that showing up, Jules, or am I off?
Yeah, you're off.
Thanks. That's better? If we call this the tangential direction, look at how we labeled these. I got to be careful here. It's going to be AC this way and A tan upwards. Well, we get negative G, which is G downwards, which actually makes sense. So notice gravity is pulling down in this equation on the right and left side. Now what's different is on the way up, it's speeding you up. On the way down, it's slowing you. I misspoke. On the way up, gravity slows you down. On the way down, gravity speeds you up. Now remember here, This is a little bit tricky. We see how critical coordinate systems are, and I know this is boring, but it's really crucial, right? Look, AT and V point opposite directions in these pictures, right? So in this case, you have to think carefully about whether they're the same sign or not. In this case, V is positive, AT is positive the other way, slowing down. When you get to the other side of the picture, V is down, AT is negative up, they're both down, it's speeding up. Did that make any sense at all? Or am I boring it? Well, both could be true. Got it? At this point, do you agree you can plug in 30 degrees and learn anything? You can plug in all these numbers and learn whatever you wanted. In particular, there's one last piece of this puzzle. We would say AC is V squared over R. Well, in this case, our radius is L, the length of the string. We've got numbers, we can plug in a bunch of stuff. Do you agree we know this, 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 this? We can get the tension in the string. If you had to guess, where is the tension in the string going to be the largest? At the bottom of the swing. Do you agree it tends to be moving fastest at the bottom? Look at this free body diagram at the bottom. Tension's up, mg's down. Wait, doesn't tension equal mg? Is there acceleration at the bottom?
Yes.
Which way? You're at the bottom of the swing. Which way is your tension? This picture's getting too messy. Let's go over to another book.
There's no tangential acceleration.
There's no tangential acceleration, but is there acceleration?
Yes,
Towards the center, right? Let's do this at the bottom on a clear FE, right? We're getting too many pictures over there. It's just getting hard to read. If this thing's at the bottom, okay, here's our star. Right? You're moving this way at some speed. I'll say V bottom because it might not be the same as that other value V, right? It's going to change as it goes around the circle. So we'll call this V bottom. But there's a force up, tension. There's a force down, mg. Are these two forces balanced? No.
Tension should be bigger.
Why? Which way is this thing accelerating?
Upwards. Okay.
Do you agree for this thing to accelerate upwards, the tension has to be bigger than mg? This is the weird part. We can't just say T equals mg when you're moving in a circle. It doesn't necessarily work. Even if you're at constant speed, but in this problem, we're not even at constant speed. We do know that we could say T minus mg equals mac at the bottom. This is not true at the top. Okay, but notice the tension is mg plus a little bit. mg plus mac. Agreed? What if we draw this at the top? If we're at the top, what direction is the tension?
Down.
The string does not push, the string pulls. What direction is the weight? Downwards. What direction is the acceleration? What force is pushing it upwards? There isn't one. That's fine. Strings don't push. So in this case, we get T plus mg equals mac. What's the tension at the top? Mac minus the weight. The weight is helping it turn. The weight is helping provide the change in velocity. Tension is smaller at the top. It's this minus something. Over here, it was this plus something. What happens if you spin this thing hella fast? What should happen to the tension if you swing it faster? Tell me. Why? Which term changes as you swing this thing faster? AC. Do you agree there's a v squared over the radius in there? So let me ask you, what if I swing this thing crazy, ludicrous fast? It would look something like it'd be MAC, and there'd be a small change due to the weight. In this case, if this is spinning fast enough, do you agree this term doesn't matter that much?
Yeah.
That's the same thing as saying, if you spin it fast enough, gravity doesn't act on it long enough to speed it up or slow it down. So if you spin a ball on a string fast enough, even if it's in a vertical circle, we could treat it as constant velocity. Even though it's not, because it's only changing by a tiny, like maybe in the third sig fig or something, right? If I was spinning this at 6,000 RPMs, the amount it speeds up and slows down is negligible. And that would be this scenario here, where the weight is negligible if you spin it fast enough. Is that making any sense? There's a lot of cool stuff in here, isn't there? All right, let's try another one. Oh my gosh. Let's look at 6.53 and make sure we understand these terms. 6.53. You could do the rest of 6.52 at home. It's a pretty good one. Take a second and look at 653. Okay. And then it's going to be party time. We get to do all these crazy demos and see the rest of the class. I love that part. We've done the work. $6.53. Okay. If it helps, I'm going to show this really quick here. Maybe I'll go here. Look at this thing right here. Here's another way you could have this thing move with constant speed, right? Is that showing up on Zoom kind of-ish? So what we've done is instead of having a ball on a string, I'm using a stiff rod, a ruler here, and then I've got this thing centered so that it's not perfectly centered. You can see there's one end that's slightly heavier than the other, but it's approximately centered. And so in this case, I hope you agree this is rotating at approximately a constant rate. So you could take a system and balance it like a Ferris wheel or a ride at the park or whatever, and you could have something rotating with constant speed. So just keep that in mind. That's kind of what we're thinking about when we're doing this problem. Is somehow we're making this thing orbit with constant speed. Okay. So let's get these terms done. 653. Somehow we've arranged the system so that this ball orbits constant speed. Maybe the system is balanced, or maybe it's like in a horizontal circle like we showed earlier, whatever. We know the distance out here is the radius. Well, if you have constant speed, v equals distance over time. Agreed? We don't have acceleration anymore. We're talking distance equals rate times time now, if constant speed, right? This only works if you have constant speed. Not the same as the last one. Well, what's the distance all the way around the circle? 2 pi r. What's the name for the time to go around one orbit? The period, which I call that weird double strike t. So I tried to make it look a little different than my pi. Okay, well, at this, I think we could find the period is equal to 2 pi r over v. All right. Now, later on, oh, so that was part A. That was all it was. Part B is omega. I want you to think of omega in this class like RPMs, rotation rate, okay? One of the units for rotation rate is RPMs. So we're not going to use those units most of the time. Obviously, in engineering applications, you would. But I want you to think RPMs when I say omega. Okay. Also notice W is not omega. When you're drawing a W in this class, make it pointy. When you're drawing an omega, make it curly. And you're going to call it W a million frickin' times, and I know that, but I'm just going to keep correcting you until gradually you're using it correctly. All right? Just watch out. It looks like a W, but it's an omega because it's curly. All right, whatever.
Mr.
Yes?
Jordan, Wyman used to call it butt cheeks.
What's that?
Wyman used to call it butt cheeks.
Yeah, it kind of looks like butt cheeks, I guess. That's cool. I was just going to call it omega. You could call it that.
My other physics professor used to call it wombo.
Called it what?
Wombo.
Wompo?
Wombo.
Boom.
Like wombo. Yeah.
Okay, that's cool too. I just call it omega. Sorry, I'm not cool like that. Yeah, and I might not be hearing right because the mass and whatever, and I'm old, but whatever. You can tell me afterwards. We'll get to it. But yeah, I just call it omega. All right, so I know that makes me uncool, but whatever. 2 pi over the period. Well, take a look. Let's plug this in. It's 2 pi over, oh my gosh, all over what? 2 pi r over v. Do you agree that's v over r? Now, I have a way to remember this. If I rearrange this, v, it's not your omega, it's r omega. So bad. But yeah, this equation, we use it a lot later on. It's not your omega, it's our omega. It's so bad, I know, but that's how it works. Okay, so far good with A and B. These are just terms that we're going to use, trying to make it clear. At some point, you could do part C later tonight and just verify you've got this. You could plug in some numbers. Notice though, this is crucial. I should mention this. What are the units of V? What are the units?
Meters per second.
Meters per second. Let's make that red so it pops. What are the units of R? So for this equation to work, what has to be the units of omega?
Meters squared per second.
No. What's that? 1 over S?
Yeah.
And that's true, but no one ever calls it that. We say radians per second because it's a trig function, or it relates to circles, which relates to trig functions. Which radians is the same thing as no units. So to be clear, you could convert from radians per second. Does anybody know how many radians are in 1 revolution? If you go all the way around a circle, how many radians?
2 pi.
Right? And so you could actually convert. We have 1 minute is 60 seconds. If you had, like, I don't know, what number did I give? We had 10.0 RPMs. That's 10.0. I guess I am doing part C. Revolutions per minute. Don't overthink it. I could say 1 minute equals 60 seconds. 1 rev. I'm going to run out of whiteboard. Oops. Pretty close. 1 rev is 2 pi rad. And I just want to show you something special about this number to help you punch those numbers in real quick. I'll do it as well. So you do have RPMs. I just wanted to show you how you can get to the standard physics unit of radians per second, or the standard calculus unit of radians per second. 10 times 2 times pi divided by 60. I got 1.04. Anybody else? Or 1.047. I know you're tired. I know it's time for a break, and we're going to do that next. But I want you to pay attention to one thing. Here's the deal. People screw up this conversion all the time when we're going back and forth, especially when we're going from radians per second to revolutions, because they'll say divide by 2 pi, and they'll forget parentheses around the 2 pi. Here's how I catch it. Look at this number. When you convert back and forth, it's approximately a factor of 10, almost exactly. 2 pi, that's 6.28 over 60, that's about a factor of 10. So whenever you're converting RPMs and rads per second, just know the answer should shift in a decimal place one way or the other. Did that make any sense? That's kind of your check on this conversion. It's a very commonly missed one, especially going the other way. Good enough? From there, once you know this is omega, right? We could get V equals R omega, just multiply by R. We can't use the RPMs, we have to use the radians per second when we're doing that. So you take this number and plug it into that equation, and we get to that answer. All right, all right. If you needed to get the period, right? We can't use RPMs to get the period directly. First convert to radians per second, right? And then you could use this equation right here. If you know omega in radians per second, that's going to give you seconds as the unit of time. All right, take that break, or if you want to punch in the numbers for the part C really quick and then take your break, go ahead and do that. All right. Circuit of motion gets pretty cool.
That's
That's the fun part.
That's
Another
right.
reason is because you
Or
can
just
literally
go back
block
to
the
like,
water supply
I
from you.
remember when I was
So the
younger,
people
my
for
parents
me,
used to
the
get
crops
get us a
died, people were
landline phone
were
service as emergencies. So they could
dying
get
of
charged
starvation.
those around.
Yeah, so
Yeah, yeah.
that's
Oh my
another
gosh.
reason why.
Yeah, I grew up with the rotary
But yeah, it's
dial.
not justifying it, but you know what I
But
mean.
you said the one where it's like just wires.
Yeah.
Like,
Yeah. I mean, we upgraded to that at one point, but.
But do you know why?
All right, all right.
Because
Let's get back into it, everybody. Let's get back into it. All right, so I don't remember, I can't remember exactly if this was on the required problems or not, but I want to look at this problem right here. This is number 6.54 in your workbook, this one right here. Jules, is it kind of on there? And I'm just going to kind of let this thing spin for a minute. And if you watch carefully, just watch those yellow golf balls for a minute. And notice, especially if I get this thing going faster, if we go really fast, let's let it maybe settle down a minute. But I hope you can see that the golf balls are changing the angle depending on where they're at in the rotation. Do you see that? In particular, at some random point in time, it's possible we get something that looks like this, right? Where the golf ball is outwards. And so what's happening here is you could think about this when you're on an amusement park ride. You feel like there's some force pushing you to the outside of the ride. But what's really happening is you're being pulled towards the center. When this happens, you perceive that you're pushed to the outside, but really, in order to maintain, good thing there's two, in order to maintain the circular motion, yeah, I'll get it, don't worry about it. You have to be pulled towards the inside. We'll talk a little bit more about this probably on Wednesday. But yeah, this is a thing called a fictitious force. But again, you can see here, oops, it's got to be pulled towards the center. I think I could probably fix this really quick. But so if you're interested in the forces on there, I just want to point out that remember, even if you're moving, well, if you're moving at constant speed, what's the tangential acceleration if this thing is going at constant speed? Okay, yes. And so then you could think, well, there's got to be some forces on the rider that are balancing this. 6.54 will address that. So in this scenario where you're just rotating an amusement park ride at constant speed, this can help you figure out what forces need to be present. So in that case, right, instead of having a tension, you have a normal force from the seat. There might be a normal force towards the center as well. All right, anyways, I'll let you kind of look at that one at home. Now I need a volunteer. Oh, you ready?
I didn't volunteer.
Oh, well then you volunteered. Yeah, come on up. This one's easy. We're going over this way. Everybody, look at problem 6.55. Okay. All right. So now all you got to do, not screw this up. Easy, right? Okay, we're going over here. Here's my approximately center on the screen right here.
Yeah.
Right about there. Okay. So now the idea here is, I didn't put water in this one. I just put some wooden spheres inside this plastic cup. So the idea is I want you to swing this thing around in a circle, and I want you to not spill the wooden spheres. Okay, so now when you do this, you got to keep it going for a while. Okay, so come over here, stand right here. And then what you want to do, if I can give you a tip, you want to kind of swing it, 1, 2, and then just start going for it, and then just keep swinging. Okay, go. Got to give it some speed. Go for it. Be aggressive. All right, now don't stop. Don't go too fast. Don't go too slow. So what's happening here is the balls do not fall out at the top of the motion. Right? Now, if you want to stop, the trick is, yeah, it's really hard to stop, right? It's easy to get it going. Okay, well, we'll see if I follow it. Let's give him a round of applause. You guys want to try this later? Get a couple more of these here. Got one? All right, there we go. All right, let's go right here. All right, let's give a round of applause there. One more round of applause. You guys want to try this after class? We'll do that.
What's the trick to stop it?
The trick is, oh, there's one too.
Oh,
Everywhere.
switch. Just start spinning it.
No, when you want to stop it, well, I'll show you here. Hey, they're everywhere.
Wait.
Most of them. Let's see if I can do it. Oh, it's more fun when you do this with kids than water, right? You gotta do the reverse. Like that. You gotta kind of let it swing up and slow down, right? Now, if you go too slow, then do that again. All right, let's just let those have a ball. All right. Hopefully I don't trip and kill myself on these. Watch out over here, will you? All right, so the trick is basically when you're slowing down, you gotta let it go past and then kind of settle it down. All right, that's kind of a fun one, right? Let's look at this one. Oh, wait, I didn't go to FBD for that. All right. So busy with these cameras.
I don't know.
What was that?
655.
655. So the trick is, if you spin this thing fast enough, we could treat this problem as constant velocity. Remember when we talked about that earlier? At the top, let's pretend it's a volume of water. Okay? So imagine we had water in the cup. What forces are exerted on the water? What's touching the water?
The bucket.
The bucket. So there's basically some sort of force from the cup. We could call that some sort of normal force from the cup or the bucket or whatever you want to call it. I think I used bucket. Are there any other forces acting on the water at the top?
Gravity.
mg. Is this accelerating if it's at constant speed? Yes. Which way? Towards the center. So now all three arrows towards the center, all three arrows are positive. So far, so good. Here is something that shows up in a lot of physics test questions and a lot of homework questions. If I want the min speed required to keep water in bucket, I want the minimum speed required to keep the water in the bucket. When you see this phrase, you're supposed to know to do something in a physics problem. Does anybody know how we can learn about the minimum speed? In particular, do you agree we don't have some way to measure this normal force unless I put a scale in there, which would be tricky. It could be done maybe, but we don't have that scale in our problem. So normal force is an unknown.
G. You set that equal to 0, right?
Set what equal to 0? Yes. Think about it. If you see this minimum speed, as you go slower and slower and slower, well, let's do this backwards. If you go really fast, do you agree there's got to be a ton of normal force, right? Otherwise, it's not going to rotate in that circle. You need, as you go faster and faster. So going the other way, as you go slower and slower, the normal force shrinks and shrinks. If the normal force goes to 0, is the water in contact with the bucket? No, it's falling out. So the trick is, if you see this, I want you to do this. We set the normal force to 0. Then we can learn something. If we set this to 0, what drops out? What's AC? What's the equation?
PC equals G.
B squared over R.
V squared over R. And notice V take a second. You're going to cross multiply by R, so you get RG and then square root it. So the minimum speed at the top needs to be square root of RG. All right. Now to be clear, if this thing was not going very fast, it would become a more complicated problem. It would be like 6.52, but this would still be true. Think about it. This free body diagram is still valid at the top, whether you're spinning it and speeding up and slowing down or not. What is the tangential acceleration at the top? 0. There's no forces left or right. All right, so that's pretty cool. This is actually valid whether we're spinning it super fast or not. We need this speed at the top. So far, so good? All right, now, oh, I know this seems pretty silly, but look at 656. I think we should talk about it really quick. 656. I know I keep belaboring this point, but I feel like it's subtle. I just want to point out the differences between these two problems right here. Look what happens if I slow down this ball too much. You see it's starting to become a projectile, right? You see the string go slack here? And it becomes a projectile, right? That was a projectile. It wasn't actually in circular motion. But look at this scenario here. I could go super slow. In this case, if you have a string, there's always going to be some minimum speed. Whereas if you have a stiff rod orbiting, you could actually have this going very close to 0 at the top. And you could actually have this velocity be super slow for a stiff rod system versus a ball on a string. Everybody got that? I only mention this because I've seen a lot of physics problems, and sometimes they try and trick you where they say, what's the minimum speed for a stiff rod at the top? Well, look at it. What's the minimum speed for this stiff rod at the top? Approximately
Almost
0. Whereas for the ball at the top, what is it? Square root of RG. Got that? All right, just be on the lookout for problems where they say, oh, it's a stiff rod rotating versus a ball on a string. All right, now we're up to this one here. Here. This thing's heavy. That's a lot. All right. Is this on? Are we visible here? Should I zoom in maybe a little bit? Okay. Got a plastic tub here. What I'm going to do is I'm going to start this thing into rotation. Okay, Angus said this works. Let's see. All right, so what you can see is the silly putty is sticking to the wall. I'll try and slow it down a little. I'll get out of the way. Can you see that silly putty sticking to the wall a little bit now? Maybe a little slower. It goes surprisingly slow. What force is holding the stick? Oh, there it just stopped. Did you see that? What force was holding that silly putty up? Friction. What force is causing it to go in circular motion? The normal force pushes towards the center. All right. Let's draw a picture of this one. This is problem 6.57. Let's look at 657. I think this one's cool for some reason. This is another amusement park ride, right? You get in a giant rotating cylinder and then they drop the floor out on you and you feel like, oh. What did I say, this was 657?
like
Rubber roll, or spinning room, or whatever you want to call
That's right.
Those are the ones where people just like stand on the sides.
it. Yes, you get, are you pressed against the wall? No, the wall's pressing you towards the center. I know this seems silly, right? You're not pressed to the outside. What does a wall do? Does a wall, well, I suppose it could be a magnetic wall and you could be wearing steel. But assuming, ignoring that possibility or somebody else, right? Walls are going to push, right? So the wall is going to push towards the center with a normal force. It's not going to pull you, right? Which way is friction?
Down, upwards.
If there was no friction, what would happen?
You fall down.
You would slide down relative to the wall, therefore friction is
Upwards.
on you. Which way does friction act on the wall?
Downward.
Downwards, okay. Any other forces here? That's a really bad letter F. Any other forces acting on a silly putty or a human being or whatever? mg, which way?
Downward.
Now, this is a little bit hard to see, so I'm just going to redraw over here. Give me a sec. If we gradually spin this thing up, doesn't this problem say gradually, gradually, gradually or something? Barrel of fun, graviton, ride people, ride gradually spins faster. I know this seems silly, but there's something that means to me. What does this statement tell me?
There's acceleration.
What?
There's acceleration.
True.
It's not constant.
What kind of acceleration? What acceleration relates to increasing speed?
Tangent.
A10. Sorry, watch out. It's like a landmine over there. Yeah, we were having a ball. There's like, they're everywhere. Yeah. I thought, man, what if a chemist comes through here? I've got to be able to trip them up, right? Okay, this relates to A10. Do you agree? Increasing speed has to do with the tangential component. Gradually. Is that a lot or a little bit? So why don't we say it's 0? The trick is if you see these words where you're gradually increasing speed, that means A10 is negligible. Is that good? That's just my keywords for cluing you in that, hey, I don't have to worry about A10 in the problem. Everybody good with that? All right. Okay, that said, what is their acceleration then? If we're at some speed, what does it say? We want the largest period. Okay. We want to have the largest possible period to keep people up on the wall. Okay, is there going to be an acceleration? Are we moving in circular motion? Yes. Is there an acceleration? Which way?
Towards the center.
There's always AC towards the center. Sometimes there's A10, but if you're moving in a circle, there's always AC. Now here's where we're going to get a little spicy. Look at this. In this case, right? This is circling around. Jules, can I see this on Zoom right now? Yeah, that's all we need, just the top. Right? I want to point out here a subtlety with the coordinate system. Do you agree that tangent to the circle would be the way the silly putty's moving, this way, in and out of the page, right? Or if you guys are on this side, it'd be in or out of the page. So I don't want to call this direction tangential, right? I would call this direction the Z direction, as in the third dimension. This direction I could call centripetal. This one I could call R hat, right? Tangential to the curve would be in the way it's moving, would either be into or out of the page. So that would be theta hat here. Now, we're not going to spend all day on this. The point being, if you're wondering why I'm not using theta hat for this direction or tangential hat, even though it's tangent to the circle, it's not tangent to the circle in the direction of motion. Got that? Whatever. So I'm going to erase these and not even talk about it anymore. All right. What do? I want the largest period. How do we get the period out of this garbage? Any ideas, thoughts? What's something we always do with an FBE right after we draw it? Force equations. Okay, give me one. Okay, equals. Is everybody cool that the normal force is the only force left, right? What else do we have? What's the acceleration up and down? How much is this thing moving up and down? 0, because it's staying up on the wall, right? So do you agree AC equals 0? What's true about these two forces then? Yeah, F equals mg. What would Horatio do? Yeah, fool. All right, so let's do it. Wait. I have the largest period to keep people up. Is this system on what frictional condition applies here? Is this about to slip? Is it slipping, or is it well under the amount that we would need to slip? About to slip, right? We want the largest period. Basically, think about this. Is a large period a fast rotation or a slow rotation? Large period, long time, slow rotation. Large period, long time, it's just barely going. If you go too slow, it's going to fall down, right? Not good enough. Okay. All right. So in this case, on verge of slipping because of this key phrase, largest period. That's the one that says we're at an extremum. Does that make sense? That's tricky. Well, what's our condition if we're on the verge of slipping? F equals US times the normal force. Excellent. So check this out. I'm just going to do a little bit of work here. Now I'm going to let Horatio do his business. What drops out? Normal force and mass. Horatio, you're a clever guy. What are we trying to find?
Period.
Where does period appear? Where is it hidden? In which variable is period somehow related?
AC.
AC. So let's solve for AC, right? AC is equal to G over mu S, is that right? Make sure I don't screw this line up. I cross multiply, well, let me just make sure. Let me rewrite this so it's clear. Yes, okay, so that I think that's right. AC is equal to G over mu S. So now, what's AC equal to? In general, it's V squared over R, right? I want to show you guys a cool trick. V is not your omega, but it is R omega. This is a really useful trick. Notice that AC, when you plug this in, you get R squared omega squared divided by R. That's R omega squared. Omega relates to the period. Am I losing you or is this okay? I'm just letting you know, like, one of the standard tricks I do on test questions to mix up the versions is I'll make one test solve for the period. A different test might have to solve for V or omega. You know what I'm saying? So basically, you got to know how to use these terms period, omega, and V interchangeably for circuit of motion. Did I make that clear? Just be aware you got to do some flipping around sometimes. Well, at this point, we got R omega squared notice that omega is equal to the square root of, let's see, G over R mu S. But that's 2 pi over the period. I don't know if you recall, omega is defined as 2 pi over the period. If you forget that, where could you find it on test A?
Front page.
Equation sheet, right? You might take a second to look back there and make sure you can find it. It's somewhere right here. This equation is written on your test equation sheet. Where's the omega equals 2 pi? Is that one not on there? Oh, that one's not on there. So you're going to have to memorize that one and scribble it on there, I think. You might have to memorize this one, but this one's on there. That's not terrible. That's pretty fundamental. You should probably memorize it. All right. Well, from here, do you agree you could solve for the period? Let's actually plug in some numbers for once. Okay, whoops. So just keep it going here. We've got, let's see, the period. That seems silly, but let's solve for it. Period is equal to 2 pi over the square root, right? Just multiply here and divide that under. So the period is equal to 2 pi times the square root of mu static R over G, right? You could just flip the square root upside down. Let's plug in some numbers. I've got one right here. Got a hockey puck here. So you can imagine, hopefully this hockey puck might have a coefficient close to 1, and it might be a little bit easier to see. We'll try that. So let's assume the static coefficient of friction is approximately 1. What are the units for mu? What are the units on the coefficient of friction? So let's just say that's 1. The radius of this tank is about, I'm just measuring, those of you on Zoom, I got to get the inner radius. The inner diameter is 44 centimeters. So the inner radius is what, 22? So the radius is 0.22 meters. Give me a good number for G. Sounds pretty good. What are the units? Are the units going to work out right? Meters cancel, seconds flip to the top, square root of seconds. This is a time. Can you punch it in for me? I don't know what I did with my calculator. So 2 times pi times square root of 0.22 divided by 9.8. I got 0.94 seconds. Is that what you got?
Yes.
Thank you. Right? Let's take a look. So we're going to run this one again. Give me a sec. All right. So I'm going to use a very technical way of measuring time, the banana method. You can use Mississippi if you choose or whatever. Does anybody have any others? Like 1 banana, 2 bananas, whatever. Let's do this. So the idea is we'll get this thing up to speed. There's our hockey puck. Does that show up pretty good? Does that show up better than the other one? Okay, so remember, we got to wait till this thing falls down. And then notice the white stripe. I'm just going to count how many bananas or Mississippis it takes to rotate after this thing falls down. Now I'm trying to adjust this gradually so that A10 is negligible, right? I'm slowing it down, but A10 is approximately 0. that crazy? Any second now. One banana. Okay, it's pretty close. Very good. Very good. Yeah. Anyways, if you want, let's see. It was about 1 banana to get around ish. So that's about right. It's approximately 1 second. Now, what could be different here? Maybe the coefficient is actually a little bit too small, right? 1 is a pretty big coefficient of friction. What do you think would happen? Let's think. What if I used something like aluminum? There would be a lot less friction. What should happen to the coefficient if I used aluminum?
I can't see.
Can't? Oh, I thought I hit the button. Oh, shoot. Thank you. That's right, because I did this thing. Give me a sec. Thank you for saying something. There we go. Right here. Okay, let's say we were using aluminum. What happens to mu?
Smaller.
Smaller. So what happens to the period?
Just
So what happens to the rotation rate? It what?
increases.
Correct. So think about this. If you're designing this, you don't know if the human beings that are coming into the fair are wearing Teflon tracksuits. So you're going to want to keep this thing cooking, right? Because you don't know if everybody's clothes are going to have the same coefficients of friction. So you're going to, right? So that's where in engineering you get into things called safety factors and stuff like that. So slightly interesting, right? I think that's cool. All right, enough on that. You guys like that one or not? I like that one. I think it's cool. Okay, let's see where we're at here. Circular motion is a lot more fun. Oh, one of my favorites. This is one of my favorites. Yeah. Hey, this is going to be a fun one. Okay, we're looking at which flies off first. Can somebody tell me? It's the next problem, I think, right? Oh. Be the next problem, right? What number is it?
6.54.
654. All right. I got it right here. Give me a second. Here's the idea. I'm going to spin this thing. Now I'm going to have to try and be very precise here and make sure all of these are exactly the same distance away. And I don't know if you can see this, but this one has 1 washer in it, so it's about 34 grams. This one has 2 washers in it, 3 washers and 4 washers. So basically, we put these washers in these little plastic tubs so that we could ensure we have the same coefficient of friction, but then we could just stack them with different amounts of weight. So my question to you is, if all of these are perfectly placed, which they're not, but they're close, which one do you think is going to fall off first? I'm going to gradually accelerate it. So A10 is 0. You think the heavy one or the light one is going to fall off first, or will it be one in the middle? Discuss with your neighbor.
Light one.
Discuss. I'm going to erase the board.
Because errors, since the light one has less mass, it's gonna end up flying off first. But like if errors was more than I.
The thing is, like, basically, we have different math. So math, sheer math, the theory of.
And but wait, what about inertia? You have inertia, you have errors. And so the cup clearly, it's just like a usually has walls that catches air. So that I feel like that's gonna take it into place. Apart from the inertia, it's the heaviest one's gonna take more energy to like fly off or like to move.
Oh, yeah.
I'm pretty sure it's gonna happen. If it doesn't, then I'm gonna be oh no.
I feel like all of them at the same time.
Just erasing the board real quick, almost there. About 30 more seconds.
Imagine all of them at the same time.
I just don't expect to hear, George that makes that noise. So. That's not.
What do you say?
All right. So in this case, let's say we wanted to learn about this situation right here. What would be a standard technique we could use to learn instead of just guessing? Let's do it. And then we'll do the fun, okay? Right here. So let's just pick a random one on the turntable. Then draw the axis of rotation. Here's a mass sitting on here. What's one force acting on the mass? Oh, great. Remind me, what problem was this? Sorry.
58.
58, thank you. Okay, what's one force? mg, straight down. Got it. To be clear, this is a side view, agreed? That's probably going to become more and more important that you add whether you're talking about a top view or a side view. This thing's rotating like this. All right, what's another force? Normal, which way? Up. Anything else? Which way?
Outwards.
Inwards.
Well, let me ask you, is this thing moving in a circle? At this point, if I was right here, what direction is towards the center of the circle? Is it right or left towards the center? So which way is it accelerating? Huh, which way does friction point?
Opposite.
No, friction produces the force towards the center. If there was no friction, right, this thing would just sit there and the road would spin underneath it and it would just levitate. Maybe you've seen this with a very large, with a superconductor or something, or a magnet over a spinning copper plate. If you haven't, let's not go that way. If there was no friction, right, this thing would just be levitating right there and this would be spinning. Right, but what's happening is the velocity needs to change direction. If I look at this from a top view, right? Think about it. Just before, the velocity's this way. Just after, the velocity's this way. You agree there had to be a force pushing towards the center? If there wasn't friction, this thing would levitate and just orbit there and do, well, it would just sit there doing nothing. Right? The friction is required to change the direction of the velocity and keep it on the turntable. We think of it as sliding to the outside, but really what's happening is the friction is insufficient to keep it in circular motion, and then it tends to move more in a straight line in accordance with Newton tends to be blah, 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 blah. Whoa. Did this make sense or not? That's weird, right?
Mr. George,
Yes.
question. What is harder to push in a large item with, that is, let's say 100-pound item with no friction, or a 10-pound item with some friction?
We could discuss that later. It's a
Okay.
good question. I'm just looking at the clock.
Yeah.
We got 20 minutes to go. I promise we can do that.
Okay.
It depends,
Okay.
right? Okay. Good enough?
Yes. I just,
And actually, you can push the same amount on either one, and who knows? It's complicated. Let's focus on that later. Let's get this one done. Good question. Really cool question. All right. In this case, help me out. Give me some force equations. How about F equals MAC? Do you agree? This is the force causing the acceleration towards the center. There's nothing else left, right? Is everybody cool with that? If it's on the verge of slipping, what else is true about friction? Yes. Agreed? Well, what are the forces up and down? What's true about these two forces? Yeah, is this the tangential direction? I would probably call this towards the center and z direction. But whatever. So in the z direction, we get what forces equal what? What would Horatio do? Right? What just dropped down? Which one flies off first?
All of them.
All at the same time. The mass doesn't matter. Do you agree? Let's take a look. Obviously, you can go on and solve for something. Now, it's critical that I accelerate this gently so that a tan is approximately equal to 0. And then I'm going to center it on the table more. Jules, am I on the right? Are we looking at it? Thank you. Oops, whatever. Here we go. And I tried to make them all the same distance to the edge, but I know I didn't do it perfectly. Oh, this sounds crusty. Ready? Pretty close to the same time. Do you agree? The slight dissimilarity is due to any imperfections in the radii, and there's probably slightly different frictions because maybe this part's been scrubbed a little more than that part, etc. Pretty close to what we expect. And they didn't fall all over the floor for once. That's like the best demo. I just love this one. Isn't that fun?
Which one fell off first?
They were all about the same. Do you agree?
Yeah.
I don't know.
I'm actually recording right now.
If we do it right
I think
over and over and over again, it's going to change which one falls off first because sometimes this one's closer to the edge. Now think about these equations really quick. This one. Here's the deal. Do you agree that this is going to give us mu static equals v squared over rg? Right? Now, if you want, you could also say, I guess we could say this is mu static equals r omega squared over g. Do you agree that either one of those is equivalent to this statement? So, in this case, do you agree they all have the same omega? Think, what does omega mean? What is omega? What does it mean?
RPM.
RPMs. They're all on the same table, which is all at the same rotation rate. Everything's got the same RPMs, but they might have different V's because they have slightly different R's. So in this case, when we move this stuff around, I guess you could say, how about we say like this, G mu static. Well, as you speed this thing up, omega gets to this critical value, and then it falls off. The ones that are closer to the edge should get there slightly faster and fall off first. So in short, the one that falls off first is the one closest to the edge. How can I prove that to you? What could I do? Doesn't matter what order I put these in, right? The one closest to the edge should fall off first, right? You agree? You good? So it's not the mass that matters, it's how close they are to the edge. Any imperfection in aligning these stupid things gives rise to one of them falls off slightly before. Agreed?
Yes.
Isn't it cool that you can actually kind of think through reality with physics equations? I think that's cool. The whole reason I'm doing physics instead of math, even though math is less work.
The only question that I still have is why isn't inertia part of the equation? Or like why doesn't it take place since they're not the same mass?
Well, it's because in this case, if we're on the verge of slipping, there's a ratio involved, right? The larger mass has more normal force, right? The larger mass should have more normal force, but it also has more friction because it's, I guess, in this case, the frictional force is approximately given by some coefficient, which is a constant times normal force, right? So as you increase the normal force, you're also increasing the friction. So we get the same amount of friction per unit mass,
Okay.
right? Because you're, right, so let me say it this way. What if we just said mu static times mg, in this case, is the frictional force, right? So if you have more mass, you also have more friction too. Got it? Or if you have less mass, you have less friction. So you thought the lighter one would fall off first, right?
Right.
Right? But you have less friction because you have less mass. And so in the end, we see that I guess the ratio of friction to normal force gives us this unusual equation, which helps us understand that. I don't know. For me, I guess what I'm saying is the mass drops out. And because I see the mass dropping out of the equation, I know that the mass matters in terms of the total quantity of newtons involved,
Yes.
but it doesn't seem to affect the rotation rate. The rotation rate in particular, if we solve this out, like that. Good. The rotation rate doesn't seem to be affected by the mass here when it's about to slip off. Cool, right?
Yeah, like mathematically it makes perfect sense, but like as you said, it's the smaller the mass, less friction. So shouldn't that less friction make it slide quicker?
Well, keep in mind, the mass also appears here, right?
Right.
So if you have less friction, you also need less friction to make it accelerate because you have less mass. Right? A smaller amount of friction can cause the same acceleration. The acceleration is the same because the friction per unit mass is the same.
Okay.
Does that help?
Yeah.
We can talk more after class. I want to get one more done. We got 10 minutes, so
All right.
we're almost there and we can talk all day if you want. Good?
Yes.
For now, for a few minutes anyway. I got one for you. Let's go back to here. I know this is going to feel like we're going backwards a little bit. Where am I at? Sorry. Let's go. This one right here. I'm just going to pull this back out. I had a question for you on this one. Remember this right here? Jules, are we showing up kind of? Oh, whoops. I have to do a couple of these next time too. That's fine. Is that hockey puck on the verge of slipping right now?
No. Or
No,
no.
right? We know it's on the verge of slipping when it was approximately 1 Mississippi. This is clearly faster than that. All right. So my question is, let's say this is rotating faster. Like let's say in our previous problem, we had some rotation rate. Let's say 6 RPMs was the required rotation rate to cause this hockey puck to stay up. If I'm rotating this at 12 RPMs, should I get twice as much friction or not?
No.
Why not? So if I'm going above the minimum rate, what happens to the amount of friction?
It shouldn't change because the masses are the same.
Exactly. Let's look at this free body diagram. I forgot to do this when we were doing it. I apologize for having to go backwards. I just wanted to mention one thing. Remember with that one? We had friction up, mg down, normal force towards the center, and there was AC. Right? What problem was this one? Sorry, I went backwards. 657. My point being this. If we crank up the speed on here, the normal force increases. But recall, that friction in the static case is less than or equal to mu static times the normal force. So in these problems, the reason I'm mentioning this right now is I want you to look out for those key words like just about to slip or largest before slipping or things like that. And almost every year on a test question, I'll sneak it in and I'll say, what if I double the rotation rate? What happens to the friction or something like that? And you're supposed to look at it and say, well, if you double the rotation rate, this should change. And what else changes? If I double the rotation rate, rotation rate doubles, are you on the verge of slipping?
No.
That's the trick in these kinds of questions, no longer on verge of slipping. And I just wanted to say that, I apologize I did that in order.
Would you also want to say that the period's cut in half?
Yeah, absolutely. You could say the period gets cut in half. Or you could say period doubles, oh wait, period cut in half, sorry. If I cut the period in half, or if I double the rotation rate, we're no longer on the verge of slipping. F still equals mg. F is less than mu static times the normal force. Did that make sense? Take a second to, yeah. It's a trick question that I love to throw in on tests, and I thought I'd tell you that I like to throw that in there. Maybe that was a waste of your time, but hopefully that makes sense. So far, so good?
Yes.
Oh, my goodness. I'm going to do one last problem. I'm going to do 6.65 because it's fairly doable. Right, 6.65, page 118. Just because I happen to have it here. Give me a sec. Make sure I'm on Zoom here. I know you can't see this very well, so let me. Real quick. Does that help? See this thing? Better? Seeing the ball here? Jules, is it on Zoom? Is it the whole thing, kind of? Or do I need to zoom out a bit? It's approximately. Are you able to see? You want to just help me out for a minute?
Yeah.
Sorry. It's tricky with cameras, right? So come up here and stand. Can you stand on that side behind the thingy? Just go ahead and hold that, right? And let's come right about there. Okay. So the idea is this. It's not a perfect, whoops. All right. Can you guys see this thing orbiting in a circle there? To be clear, is this on Zoom at all, Jules? Okay, so notice there's a circle here like this, and it's kind of hard to visualize this. This is called a conical pendulum because you can kind of imagine this string is tracing out a cone here. And now it's probably a little bit elliptical, but you get the idea. It's kind of good enough. All right, so this is the problem we're going to try and understand on the board. It's a little bit different than some of the ones we've been doing, but some aspects are the same. All right, let's give him a round of applause there. All right. Keep that in your mind as we look at this last problem today. Now let's just go board 6. I want to try and get a feeling for this one. Oops. Gosh, I'm gonna have to spend some time cleaning up this room afterwards, huh? You guys like the demos? Is it more fun to have them or not?
Yeah. Yes.
I feel like it's really hard to visualize these problems without, even if the demo kind of doesn't work right, it gives you a better feeling. So hopefully that works for you. What did I say, 665? Yeah. All right. There's a ball, it's attached to the ceiling of some kind. And we see it going in this weird circular path here. Sorry if it's not a perfect path. All right. The idea is This is the axis of rotation now. I know this is hard to see. But again, maybe if I draw the circle here, it's solid, it would be a little bit easier to see. This thing is going in some circular path like this. Does that make it a little bit easier to visualize here? It's hard. Drawing in 3D is not easy. So in this case, which way is that ball accelerating? What's that?
Towards the center.
Towards the center of the circle. Show me with your fingers. It's at the right edge right now. Which way is it accelerating? Yeah, this way. Towards the center is towards the axis, which is right in the middle. It's kind of a weird problem, right? So this direction is towards the center. All right. What forces act on the ball? MG, I heard MG. What's another one?
Tension
Which way?
to an angle.
Yeah. Now, in practice, usually this is the angle we're given. Is that the one I gave you?
Yeah.
And in practice, just so you know, strictly speaking, we want to go to the center of the ball. So we're going to the center of the ball. That's where the center of mass is. More on that some other time. But so if that's theta, what's this angle down here? If this is theta, what's this?
90
So what's this angle up here? Theta. Does that make any sense at all? Theta, alternate whatevers. That's a very technical geometry term. Got 3 minutes. Getting it done. I would call this towards the center. This, the z direction. We're accelerating towards the center, AC. Give me one force equation in the z direction. Give me a force equation in the z direction. T adjacent, T cos. Good job. You caught it. T cosine theta. Positive or negative? What else? Minus mg equals 0. So do you agree I could just say equals mg? You good with that? Right on. How about the centripetal direction?
T sine theta.
Positive or negative?
Positive.
Right? Going towards the center, going towards the center, going towards the center is T sine theta. What's that equal to? So notice that Horatio's trick works pretty well on these types of problems. Have you seen that a lot of problems it's convenient to take a ratio here? That's the whole stupidity behind. Now, what if you wanted to figure out, I guess, let's think big picture here. You're going to get a problem on your next test that has some sort of circular motion. And there's going to be some different planes of attack. But one thing that we've seen that's common to everything today, what's our first thing that we've been doing on every single problem? Free body diagram. Draw your forces. Make sure you think carefully. Then we can write our force equations. Next, read the question, solve for something. Finally, remember that AC can be written in a couple of different ways. It's R omega squared on your test equation sheet. Or it's V squared over R. And then finally, we know that 2 pi, whoops, let me just put this here. 2 pi over the period is equal to omega. One last thing, use radians per second for omega. This is kind of the tricks that work for all of the circular motion problems that we've been doing today. Draw FBs, write force equations, use some of this crap, answer something, do algebra. Did that make any sense as a summary? Got a couple more for later. Yep, we'll just save for next time. We'll do it next time.
And then the only thing with a problem like this is that the radius of the circle is going to be a trigonometric component of the. length
Oh,
of the-
yes, thank you for pointing that out. We should mention that right now, and I was such in a hurry to get to that summary. What's the radius here? He's pointing that out. Look at this triangle. Thank you for saying that before I forgot. That's really good to say. If this side's L and this side's theta, what's the radius? L sine theta. Did that make sense? Now, this is really important. Check this out. Check this subtle trick out. If you can get used to doing this, you'll probably have more success. I draw an FBD here and a separate picture for figuring out the radius and stuff over there. If you try to get the radius on the same picture as your FBD, it gets cluttered and you make mistakes. Again, separate picture for geometry and FBD. We're going to hammer that in chapter 12. All right, thank you for bringing that up. I apologize, I didn't say that earlier. Good enough for now? We'll pick up here next time. We'll do a couple more circuit of motion problems. We'll talk about frictional forces. And then we're going into chapter 7 next time. So you got to have the next workbook by next time. Got it? All right. Oh my goodness. That was intense. What'd you think of that, Alexis? Oh, you got the question right. Oh, go ahead.
So I can't make it to lab this week because of the swim meet.
Okay, okay.
Should I email it to you or?
Yeah, email me that information. So you'll take a 0 for this one. And we discussed that, right? Yeah, and so, but then you can do the makeup at the end, right? So, and then the other one, I think you were gonna miss another one later, right? Yeah, so on that one, we'll, it turns out, I guess me being sick worked out for you because I'm doing 2 1-week jobs, so then it's less. Thank you. Which is good. So it's almost like a normal, yeah. Is that good? So, yeah.
Do you purposely get dressed that stick then?
That's right, that's right, that's right.
Yeah.
Right.
But yeah, it's like.
What's that sound I hear? Is that you, Alexis? I'm trying to, hold on. Oh, sorry, the volume. Go ahead, Alexis, sorry.
Oh, yeah, it was a lot.
Yeah, so what do you think? Did you get some of that on Zoom or not?
Yeah, yeah, everything went well on Zoom.
All right, sounds good. All right, I'm gonna end the stream then, okay?